This is the second lecture of chapter 14, which deals with free radical substitution reactions. In this presentation, what we will be concentrating on is, number one, the chlorination of alkanes, the bromination of alkanes. Notice these are two halogens that are used here, chlorine and bromine. Then we will concentrate on the stereochemistry involved in the chlorination reaction or the halogenation reactions. And lastly, we will look at the application of free radical substitution reactions to synthesis. As you know, synthesis is a very important aspect of organic chemistry because that is how we make larger molecules from smaller starting materials. So let us begin. Let us first of all look at substitution reactions again. And this one in particular is the free radical substitution reaction. So let us look at methane, for example. There are 4 hydrogens here in methane. So in a free radical substitution, you'll see why I'm emphasizing radical in a minute, because that is an integral part of the mechanism and is an intermediate. So in the presence of energy such as heat or light, chlorine reacts with an alkane. Remember here, an alkane is a hydrocarbon in which all the carbons have 4 bonds to it. In other words, they are all sp3 hybridized. So for the substitution reaction, 1 hydrogen is substituted for a chlorine to give chloromethane as the organic product. As you can imagine, the other product is, of course, HCl. So if given cyclohexane and you're asked to predict the organic product for the reaction with chlorine in the presence of energy in the form of heat, what you should be able to predict here is that this is the line angle representation of cyclohexane. You should recall that there are 2 hydrogens here, 1 here and 1 here. So substitution of one of these hydrogens with a chlorine will give us our organic molecule chlorocyclohexane and the inorganic molecule HCl. Let us look at the mechanism, because as you know, the mechanism is an important aspect of organic chemistry. Why? Because a lot of times we carry out a reaction and we get unexpected products. We do not get, or we get in addition to our target molecule, we get unexpected products. One way of understanding the source of unexpected products is by knowing the mechanism. So let's look at the mechanism for the chlorination of methane. The chlorination of methane, let's look at the mechanism. First, energy in the form of heat or light is needed. What happens here is that it will break this CCl-Cl bond. Remember, that's a covalent bond with 2 electrons. It's a single covalent bond, 2 electrons. So breaking this bond here, 1 electron will go to the chlorine and the other electron will go to the other chlorine to generate chlorine dot or radical and another chlorine dot radical. So now you can see the importance of chlorine radicals in this mechanism. This first step is called the initiation step. Why? Because we have initiated the radicals. Chlorine radicals here are very reactive. So as you can imagine, in the presence of methane, it's reactive because it has one electron. It needs one more electron to form a bond. Here is a bond with 2 electrons. So if we take 1 electron from that single covalent bond, we get here HCl. What's left behind is a radical. As you can see here, the arrows to indicate those electron movements. Now you can see why in a mechanism, the question typically states using arrows to indicate electron movement, propose a mechanism. Here are arrows. This time it's single barb arrows because it's 1 electron movement at a time to show how the bonds are formed. The methyl radical that's produced, as you can imagine, it's an intermediate, very reactive because it has a lone pair of electrons right here. Here is a single covalent bond with 2 electrons. If we can get 1 electron from that bond and with this other electron from the methyl radical, we can form here a new covalent bond, and the other electron goes onto the chlorine to form chlorine radical. As you can imagine, that step is called a propagation step because radicals are generated. In this case, it is the chlorine radical. The last step of this reaction, the chlorine radical, 1 electron, and the methyl radical, 1 electron, if they come together, we can form a bond right here, and here is that bond. Here are the electrons, the arrows to show the electron movement. This electron comes in to form a bond, this electron comes in to form a bond, and here is the bond. That step is called a termination step, as you can imagine, because the radicals come together to form a neutral molecule, in this case chloromethane. Let us look at the formation of unexpected products. So from the previous slide, you would expect to get chloromethane as your product. But it is possible to form here dichloromethane as one of the products. Let's see how that is formed. So if we have chloromethane that's formed from the previous reaction, we still have chlorine radicals present. It's reactive because it has 1 electron. Here are 2 electrons in this bond. If 1 electron comes over to form a bond here, we can get HCl. What's left behind is a radical. In this case, it's a chloromethyl radical. As you can imagine, this chloromethyl radical can react with another mole of chlorine using 1 electron from this bond, and this odd electron from the chloromethyl radical will form this bond right here, and the other electron goes to form another chlorine radical. But the bottom line is we have formed an unexpected product here, which is dichloromethane. Another unexpected product is ethane. Notice this product here does not have chlorine in it. It's just ethane, hydrocarbon. That's formed whenever we have a methyl radical and another methyl radical forming a bond right here. Notice again, these arrows are used to indicate electron movement to form this bond right here. So as you can imagine, whenever these reactions are carried out based on the reaction condition, if there's a large excess of chlorine, you would get polychlorinated product. And of course, if the concentration is not as much, you tend to get your monochlorinated product. Let us look at some reactions here in which chlorine is used in the presence of heat as a source of energy. So the question is, if we have here propane in the presence of chlorine, what are the possible monochlorinated product? So we're looking at monohalogenation, in this case monochlorination. As you can imagine, here are 2 hydrogens and here are 3 hydrogens. So the hydrogens here are different from the hydrogens here. So this is one product and this is another possible product. This is a secondary carbon with secondary hydrogens, as you can imagine here. And this is a primary carbon with primary hydrogens. Let's look at this molecule. This carbon is equivalent to that carbon. It's a tertiary carbon. This methyl group is equivalent to this, same as this, same as that, because it's a primary carbon. So upon substitution of one hydrogen with chlorine, you'd expect to get 2 possible products. Here's one and here's the other. This product comes from this hydrogen, a substitution here, and this product comes from a substitution of one of those hydrogens. Let's put it here so you can see it. That hydrogen gives that as a product. And lastly, butane. We have here carbon with 2 hydrogens and carbon with 2 hydrogens. Those are equivalent. A methyl and a methyl, these are again equivalent. So therefore we would expect 2 products, this product as one from substitution here, and this product as the other from substitution right here. So you should be able to predict the monochlorinated or halogenated products for the reaction of a halogen with an alkane. Let us look at this reaction here. The reaction of propane with chlorine in a little more detail here. So drawn out, given the expanded structure, you can see here this carbon is bonded to a hydrogen. So therefore this hydrogen here is a secondary hydrogen, which means that this bond here is much weaker than this bond here, which is this hydrogen is bonded to a primary carbon. So again, this is a secondary carbon and this is a primary carbon, which means that this bond here is stronger than this bond which bonded to the secondary carbon. So what happens here is that chlorine will carry the substitution for this hydrogen, as shown here, and for this hydrogen, as shown here. However, you notice here that it's not equal. There's a 50, slightly more of the 2-chloropropane compared to the 1-chloropropane, or slightly more of the product where this bond here is broken to give this as the product compared to this bond, which is a primary, to give this as the product. The bottom line is they're not equal. Why? Because this bond here is weaker, as we said earlier, because it's a secondary CH bond compared to a primary CH bond, which is stronger. So there's slightly more of the 2-chloropropane compared to 1-chloropropane. However, if you're doing a synthesis and you get 55% yield, if you're trying to make this as your target molecule, that is not good, because you've lost 45% of your molecule in terms of unwanted products, side products. So that's not good using chlorine. But look at this, using bromine, putting on a halogen, in this case bromine, in the same position gives 98% yield. So that's a good yield in terms of putting on a hydrogen on this carbon, or substitution of a hydrogen for bromine right here. 98%. Let us see why that occurs. Now we'll have to look at the bond dissociation energies. The energy required to break this bond here, and the energy required to break that bond to produce the radicals. 58 kilocalories per mole is required to break this bond to give here the chlorine radicals. Far less, 46 kilocalories is required to give the bromine radicals, which I write like that. Since this requires less energy, it is implying that the bromine-bromine bond is weak, which means that the bromine radical that's formed is stable. We know why it's stable, because it is large. The chlorine-chlorine bond is stronger, and of course this is now more reactive compared to the bromine radical. So that is key. The key here is the bromine radical is stable and less reactive compared to the chlorine radical, which is not as stable and more reactive. Let us apply that concept. So if we have this molecule here, and here is our CH bond to the secondary hydrogen, bromine being less reactive, it will prefer to bond with the weaker CH bond. The weaker bond here, because it's less reactive, so it will bond to the weaker CH bond to form the secondary radical, or the more stable radical. That does not mean that the other reaction does not occur, so the bromine can bond with can break the primary CH bond here, but with much difficulty, because it is a stronger bond, and this is not reactive. So that's why this is formed in small amounts, because it's less stable. Bottom line is we have more of this forming, and that will lead to the products as shown here. So as you can see here, the bromine radical in a termination step will bond to the secondary radical that was formed to form here the 2-bromopropane as the major product. As the minor product, which is 2%, the primary radical, if it's formed or formed in very minor quantities, will bond here with the bromine to give here 1-bromopropane, which is now the minor product. But the bottom line is that's the major product, because bromine is less reactive and will be selective to react with the weaker CH bond. So here is a summary of the concept we just covered. So here is butane again, and if you're asked to predict now the major product, this time using bromine and heat as energy, of course we could use light if we wanted to, this is definitely the major product. Why? Because this carbon here has 2 hydrogens, which makes it, and it's bonded to 2 other carbons, which makes it a secondary carbon, and this is a secondary CH, weaker bond right here. So therefore this is the major product. Let's look at this molecule. This has a hydrogen here, don't forget. This carbon here is a tertiary carbon because it's bonded to 3 other carbons. So this is a tertiary CH bond right here. And of course, as you know, that's the weakest. A very weak bond. I wouldn't say the weakest, but it is a weak bond. So this is your major organic product. Let's look at this molecule. As you can imagine, here is a tertiary carbon and here is a secondary carbon. So a substitution reaction, a free radical substitution reaction, will give this as our major product here. Major product. So you should be able to predict the major product using bromination. I should quickly point out, however, that the stereochemistry here is very important. So you will recall that the carbon radical is flat and it's sp2, which means that the bromine can come in from the top or the bottom. So if we have three different R groups here, adding a fourth group will make this carbon a chiral carbon, and we'll have what's called a racemic mixture here. So again, the product is a mixture of enantiomers. As you can see here, what we have here is butane. Here is a CH2 and a CH2 here. And the reaction with bromine will give this racemic mixture here, the R and the S. Notice the stereochemistry as indicated by the dash and the wedge. Two possible products. In this case, it's racemic based on the stereochemistry for the addition to the radical. Here's another example. Here is the site of reaction. So we have here a hydrogen, and in this case it's a tertiary carbon, which means that this bond here is a tertiary CH bond, which means that bromine will substitute right here for this hydrogen, and we'll have two products, racemic mixture, because we have one up and one in the back. So look out for the stereochemistry. You will get a mixture, a racemic product. Let's see if we can apply this concept here. So, if you had this molecule as your starting material, starting molecule, okay, and that's what's that? Methyl cyclohexane. If you wanted to substitute this hydrogen for a halogen to do some other reaction, the question is, would you use a chlorine or would you use the bromine? As we have just discussed, you would prefer to use the bromine because it is more selective for the tertiary CH bond. So this will be the major product. If you use chlorine over here, you're going to get a mixture of this product and substitution on the other carbons. So once again, whenever you're doing synthesis, if you need a halogenated product right here or a halogenated product period, look at the molecule carefully and determine if you need bromine or chlorine. You may say, well, why not let's use bromine all the time? But let's see. If the molecule is symmetric, like cyclohexane, there's only one product. And since bromine is more expensive than chlorine, it's preferable to use chlorine to make this halogenated product compared to bromine. Notice the same halogenated product, but in this case it's symmetrical, so it does not make a difference in terms of reaction, but it makes a difference in terms of cost because chlorine is cheaper than bromine. Okay, let us look at another concept here. If you have an allylic CH, as shown here, this is an allylic CH right here. As you know, that bond is very weak because it gives the allylic radical, which is very stable. But here's a potential problem. In the presence of bromine and heat, of course as a solvent, this double bond here will be involved in an addition reaction, as we have discussed before. An addition to alkene. So this is a possible addition product. In addition, you will get the desired product, but you'll also get a mixture. So if you're doing a synthesis, this may not be the best route here. Let's see. Over the years, chemists have determined another molecule that can carry out selective bromination at the allylic position. That molecule is called NBS, or N-bromosuccinimide. As chemists, we'll understand if you just write NBS. So if you use NBS and heat, you'll get here the substitution at the allylic position as the major product. The mechanism is in the book, so you may want to read that over again. The same thing with the benzylic position. If you need the bromine here for one of these hydrogens here, NBS and heat will give that substitution in the benzylic position. So again, you have a choice here in terms of chemicals. The best chemical for the allylic and benzylic substitution is NBS. That doesn't mean that bromine and heat won't work, but it's not the most efficient way to carry out that substitution. Let us look here at application. So in this slide, what we'll try to do is show how to carry out the following transformation. As you know, there's always a question on the quiz or on the test to have you show that you can apply the concepts that's studied. So here is a question like that. So let us see the approach. The approach that I'm suggesting is, as chemists and scientists, carry out the observations carefully and come up with a strategy. I suggest working backwards. So start with your target molecule over here. Your target molecule has a functional group, and that's a ketone functional group. The question you should be asking is, how do I make a ketone? Remember, we're working backwards, or retrosynthesis. How do I make a ketone? We can make ketones by oxidation of an alcohol, secondary alcohol, and here is the alcohol. So if we had this alcohol, we can carry out an oxidation. You just have to come up with a good oxidizing agent, and you have your target material right here. Now comes the question, how do I make this alcohol? Because that is definitely not my starting material. So how do I make this alcohol? You can make alcohols, as you know, by addition to an alkene. So if we had this alkene over here, we can add water across the double bond right here to get hydration. In this case though, be careful. This is an anti-Markovnikov addition. So you'll have to be careful to select the proper reagents. The next question you'd ask yourself is, how do I make alkenes? You make alkenes by elimination reaction. So if you had a bromine here, and of course hydrogen is here, you can make this as your alkene right here. This of course is not your starting material. So how do you go from this to this? It's a selective halogenation, bromination. You would not use chlorine because you want a high yield of this molecule here as your product. So that's why you use the selective halogenation, which is bromine or bromination. So let's put this all together and come up with the reagents. So what we have here is, for the substitution reaction, we use bromine and heat because that's the selective halogenation bromine to get the alkyl bromide. High percentage of that. For the elimination reaction, we use KOH, alcohol, and heat. Notice small base. If you used a large base such as LDA, the double bond would be formed here. But since you want the double bond here, you use a small base to get the more stable double bond or alkene, which is the ZF product. To go from your alkene to your alcohol, it's an hydration, but as I pointed out, it's a anti-Markovnikov addition. So here are the reaction conditions for the anti-Markovnikov hydration. Notice two steps, step 1 and step 2. So you'll have to indicate separate steps. The last portion of the synthesis is going from an alcohol to a ketone and oxidation. A common oxidizing agent is potassium permanganate. So this is what I would expect as the solution for that question that asks, how do you transform this molecule into the target molecule given? Lastly, let's look at an application here of halogenated compounds. As I point out here, each year several metric tons of organohalides in the form of chlorofluorocarbons are released into the atmosphere. Why is that so important? These chlorofluorocarbons form refrigerants. They act as the main coolant for your air-conditioned units. Of course, as you know, it's also known as Freon. This particular one here is Freon 12. In the presence of UV light, so if it should escape from your air-conditioned unit, if it escapes and gets into the environment, UV light, which is of course all around, breaks the bond right here, a homolytic cleavage, to get this radical and the chlorine radical. Chlorine radical is of course very reactive, so it reacts with ozone using this reaction here. The main point here is that it will deplete the concentration of ozone in the atmosphere. Of course, as you know, ozone is a reagent that protects us from UV radiation. So the refrigerant or the chlorofluorocarbons act as depleting the ozone layer, and that's why they have been banned from use in refrigerant and air-conditioned units. So that gives you a practical application of chlorofluorocarbons, and you could read more in your textbook. I think this is the last slide. So go ahead and review this material. Again, you may want to read along in your textbook as you go through these PowerPoints and the lecture. Work lots of problems. I posted the tutorial questions already, so try to work them through and apply the concepts that we have studied. So we'll have a quiz again this coming Thursday. Don't forget, next week, Thursday, the 11th of February, is our first midterm exam, so keep practicing. Okay? Continue to study hard. Okay?